Okay, let's move on. In the last class, we began to look at the band structure of two-dimensional extended solids. And first, we looked at the most simple two-dimensional extended solid that we can imagine, and we said that this most simple two-dimensional extended solid would be a square lattice of hydrogen atoms. Why a square lattice of hydrogen atoms? That's because hydrogen atoms are the most simple atoms, and a square lattice is the lattice with the highest symmetry possible. So we also said that in order to describe the band structure of a two-dimensional lattice, we have to introduce two wave vectors, one pointing into the first direction. We can define the first direction the x direction, and the second one to be the ky wave vector pointing in the y direction. So these two k vectors would define corresponding lattice to the original square lattice, whereby this corresponding lattice would now be in the reciprocal space. And in that reciprocal space, the k vectors k1 and k2, kx and ky would stand perpendicular to each other. So we then thought, what would be the crystal orbitals in these two dimensions? And we said that, well, we can first look at the point in the reciprocal lattice in which both kx and ky are equal to 0. So this point is called lambda. Okay. So lambda is the origin in our reciprocal lattice, whereby we can define also a reciprocal cell, which is defined by the cell in the reciprocal space in which k1 and k2 vary between 0 and pi over a respectively. This cell is also called the Brillouin zone within the reciprocal space. So it's nothing else but the unit cell within the reciprocal space. Okay, so then we said, well, at kx equal to 0 and ky equal to 0, we neither flip the algebraic signs of the 1s orbitals in x direction and in y direction. Okay, so that means that, well, all algebraic signs remain positive in both directions. Basically, all 1s orbitals have positive algebraic sign. One can immediately see from that the crystal orbital at that point lambda is entirely bonding. Okay, so now in the next step, we can go to kx is equal to pi over a and ky remaining 0. Okay, so then we arrive at a point called chi within the Brillouin zone. This is this point here. Okay, ky has now reached its maximum value within that unit cell, and well, k2 is equal to 0. So now that means that now in x direction we have to flip the algebraic sign of every other 1s orbital, whereby in y direction we do not flip the algebraic signs at all. So you see that this results in this crystal orbital here. So we can again evaluate the bonding situation of this crystal orbital here, And we see that it is non-bonding because we have only anti-bonding interactions in X direction and only bonding interactions in Y direction. Okay, so now we could also do the opposite. We could say that, well, we go to ky equal to pi over a and keep kx equal to 0. Okay, then we would arrive at this crystal orbital here. Now in X direction, the algebraic sign isn't changed at all, but in Y direction, the algebraic sign of every other orbital would be changed. Okay, we can see that also this crystal orbital here would be a non-bonding crystal orbital. Okay, so now because of symmetry, the point chi associated with this crystal orbital is symmetry equivalent to this point chi associated with this crystal orbital. Therefore, in the band structure, we only have to consider one of the two cases. Okay. Okay, so finally, we could also think about what is the crystal orbital in which both kx is equal to pi over a and ky is equal to pi over a. All right, so this would define this point M here within our unit cell within the reciprocal space. Sorry? Sorry, I do not understand you. Can you please repeat?
Sorry, it wasn't a question. My bad.
It was just a comment into the space. All right, good. I just couldn't understand it correctly. All right, so now at the position M, our crystal orbit looks like that. You see now that the algebraic sign of every other 1s orbital is changed in X direction as well as in Y direction. So now you see that this crystal orbital is obviously completely antibonding. Okay, so now we can actually define our band diagram, okay, which is now depicted here. Okay, so we have here the energy of our crystal orbitals that will depend on how bonding and how antibonding the crystal orbitals are, versus, well, the k vector in the reciprocal space. Okay, whereby you can see this on this axis here, that we will first go from point lambda to x, and then from x to m, and then finally we will go back from m to lambda. So now we said that this orbital here is completely bonding, so we will start at a low energy. So these two orbitals here at equivalent point x is equal to non-bonding. Okay, so we are actually going up from a completely bonding situation to a non-bonding situation here. Okay, and then the next step, we go from point chi to point M. So that means that we go from a non-bonding situation, to an interbonding situation, the most interbonding situation possible. So we go further up in energy. So now as we return to the point lambda, okay, whereby we are going now directly from the point M to the point lambda, we are going from the most interbonding situation back to the most bonding situation. Okay, so this would represent now our band diagram, in the two-dimensional space, 4 is square lattice of hydrogen atoms. Okay, of course we can also think about additional crystal orbitals. Okay, so for instance we can think about, well, what's the crystal orbital halfways back from the point M to the point lambda. So that would be the crystal orbital, which would actually be located here. So in this case, basically you would arrive at this crystal orbital here. So you would not flip the algebraic sign of every other 1s orbital in both directions, but you would flip basically the algebraic signs of pairs of 1s orbitals, or every other pair of 1s orbitals. So this would be positive, this would be positive, this would be negative, this would be negative. To minimize energy, the algebraic sign of these crystal orbitals here would become 0, and you would arrive at a crystal orbital in which basically you have 1s orbital positive, the next 1s orbital has no amplitude, and the following 1s orbital has a negative amplitude. Okay, then this would be followed by another 1s orbital with no amplitude, followed by another 1s orbital with positive amplitude, and so forth. And that situation you would have in both dimensions, in x direction as well as in the y direction. Okay, so we will immediately see that this orbital here has also essentially non-bonding character. Okay, so you have here opposite algebraic signs, but of course now these orbitals are so far apart, yeah, that there's practically no orbital overlap. Okay, so you would have some weak interbonding interactions here, yeah, but you would also have the same degree of positive interactions, for instance here in this direction, so that these and these would also cancel out, resulting overall in a non-bonding orbital. Okay, so that non-bonding orbital you would find here halfways, here approximately at this position, in between the most interbonding and the most bonding crystal orbital at the points M and lambda respectively. All right, so you could also think, for instance, about the case in which kx is equal to pi over 2a and ky is equal to 0. Okay, so this means that you would actually go halfways to the point x in this direction. So this crystal orbital would actually be located here. So now, in this case, you would have basically a non-bonding situation in x direction, just because you introduce these nodes here in which the amplitudes of the 1s orbitals would be 0. There would be interbonding interactions here, but there's essentially no orbital overlap, making the situation essentially non-bonding. Whereas in y direction, you still have bonding interactions. So you would still overall have a bonding crystal orbital, but of course it's not as bonding as this crystal orbital here. Okay, so that would be here, this crystal orbital that would be here within the band structure. Of course, you could also look at the other case, have kx equal to 0 and ky being equal to pi over 2a. Okay, then you would go halfways into this direction. You would have bonding interactions in x direction and essentially non-bonding interactions in y direction. Again, that would result in a weakly bonding situation overall. Again, this crystal orbital here would be just a 90-degree rotation of this crystal orbital, so they would be symmetry equivalent. So you actually only need to consider them once in the band diagram. Okay, now in the next step, let us go from the 1s orbitals to p orbital. So let's assume our square net is not just made of hydrogen atoms, but also atoms that have p orbitals. So that again could be, for instance, fluorine atoms. What would be the band structure in 2 dimensions for the p orbitals? Okay, let us first look at the px orbitals and the py orbitals at the point lambda. Okay, so the px orbitals, they point into x direction, the py orbitals point into y direction. So at k equal to 0, for both kx and ky, implies that neither in x direction nor in y direction we flip the algebraic signs of the orbitals. Okay, so that means that the px orbitals will line up in x direction. Okay, and they also line up without any flip of algebraic sign in y direction. All right, now you can see that there's sigma orbital overlap in x direction, and you see that the sigma orbital overlap is essentially is only interbonding. Yeah. Whereas actually in y direction we have pi orbital overlap, which is bonding. But of course the sigma orbital overlap counts more because it's stronger. So for that reason, this crystal orbital here is interbonding overall. So now what about the py? For py we have the same situation. The only difference is that now we have the interbonding sigma interactions in y direction and the bonding pi interactions in x direction. Okay, but overall we have the same degree of interbonding interactions as we had for the px orbital. Okay, therefore both of these orbitals are interbonding. So now we can go from the point lambda to the point x. Okay, so we can first make kx is equal to pi over a and ky remaining 0. That means that we have to flip the algebraic sign of every other px orbital in x direction. Okay, so you see that this one here, that second one, is flipped relative to the first one, and the third one is then again flipped relative to the second one. Okay, so you can immediately see that in x direction, this results in the most bonding situation possible. Okay, so now in y direction, we do not flip the algebraic signs of the orbitals at all. You can see that because of that, the pi interactions along y remain bonding. So now we have bonding sigma interactions and we have bonding pi interactions. And that's basically the most bonding situation we can create. So certainly this crystal orbital here will be strongly bonding. So now what about the py? So now as we flip the algebraic sign of the py orbitals in y direction, okay, we actually make the pi interactions interbonding. Okay, so now in y direction we do not flip the algebraic signs of the wave function, And you see that for that reason, the interbonding sigma interactions remain, okay, here and here. So now we have both interbonding pi interactions as well as interbonding sigma interactions, making this crystal orbital the most interbonding crystal orbital that is possible. All right, now we could have also done the opposite, and that's actually shown here. We could have also defined ky to be equal to pi over a and kx remaining 0. So that would now render the px orbitals to be interbonding. Okay, you see you have interbonding sigma interactions as interbonding pi interactions. Whereas for the py orbitals, we would have a completely bonding situation. You see that the pi interactions are bonding and the sigma interactions are also bonding. Okay. Again, that point y is symmetry equivalent to that point x. We can actually just rotate that crystal orbital here by 90 degrees, and then it becomes this, and rotate this crystal orbital here by 90 degrees, then it becomes this, so that we only need to consider one of the two cases. So finally, we can also go to the point M. So at the point M, kx is equal to pi over a, and py is also equal to pi over a. So now we must change the algebraic signs in both directions. Let us look what that means for the px orbital first. So we see that we certainly create bonding sigma interactions as we do that, but we create now interbonding pi interactions. So sigma interactions are stronger than pi interactions. So for that reason, this crystal orbital here will be bonding, but it will not be as bonding as this crystal orbital here. All right, so we can do this now for the py too. Now, for the py, we create, well, now interbonding situation here in x direction, where the pi interactions are, and we create a bonding situation here in y direction, resulting also overall in a bonding situation. Okay, and we would expect that the energy of this crystal orbital and the energy of this crystal orbital here are exactly the same. They are both weakly bonding. Okay, so now with that information, we can construct the band diagram for the px and the py crystal orbitals. So we can start out here with these two. So we determine that these two are both interbonding, even though not the most interbonding ones possible. So now as we go from lambda to chi, we create, well, this most bonding orbital here, which is lower in energy, and this most interbonding crystal orbital, which has a very high energy. All right. So now as we go from chi to m, okay, we create these two crystal orbitals, which are energy equivalent and which are both weakly bonding. Okay, so these are being located. These are located here. So you see that these two are energetically higher than this most bonding one, but energetically lower than these two, which are weakly interbonding. Okay. Of course, as we went back from m to lambda, we go back to these two, which are identical to these two. All right, so we can now also think about, well, the pz orbitals. Okay, so now the pz orbital is then perpendicular to the xy plane. Okay, so for that reason, they act pretty much the same as the 1s orbitals, meaning that as we go from lambda to x, the energy is actually increased, and we have a non-bonding crystal orbital. And as we go from lambda to m, we have, well, the most interbonding situation. And as we go from m back to lambda, we again go back to the most bonding situation. Okay, so now let us go from the hypothetical cases in the next step to real cases. Okay, let us discuss the band structure of a real two-dimensional extended solid that makes a square lattice. Okay, and such a structure is, for example, the compound barium stannate Ba2SNO4. So first, let us understand the structure. So this structure is a layered structure, and precisely you have here layers of corner-sharing SNO6 octahedra. Okay, so you see here one such layer. So you see here there are tin atoms in the center of these octahedra, and these tin atoms are then surrounded octahedrally by 6 oxygen atoms. Okay, you can easily see that one sheet has a square as its unit cell. Okay, so now, of course, in the real crystal structure, you would have multiple of these layers stacked. You can see this here. And in between these layers, you would have your barium 2+ ions. Okay. So in the following, we will make a qualitative band structure, will develop a qualitative band structure for one of these sheets, okay, whereby we will make here the simplification that, of course, the orbitals within that sheet would also interact somehow with the barium ions, and we neglect that, yeah, in the third dimension. And furthermore, we will neglect all the interactions from the 2s of O and further within one layer, and also all pi interactions within one layer. Okay, so we will consider only the p orbitals of oxygen, okay, as the valence orbital, and we will only consider the 5s and the 5p orbitals of the tin as valence orbitals of the oxygen. We will neglect that the oxygen has also 2s orbitals available to make bonding. All right. Now let us start with the interactions between the 5s orbitals of the tin and the 2p orbitals of the oxygen. All right. So now we again have to consider the crystal orbitals at 3 points in our, well, reciprocal unit cell, the points lambda, the point chi, and the point m. Okay. So now at lambda, kx has to be 0 and kyx has to be 0. And that means that we do not flip the algebraic signs of the wave functions for all the orbitals that we consider here, which is in this case the 5s of the tin and the 2p of the oxygen. Okay. So now in the XY plane, and because we only consider sigma interactions, we only need to consider the px orbital of oxygen and the py orbitals of oxygen. Okay, so you see here, well, several square unit cells within a sheet. Okay, so in the center of the square, we have the tin, and then the oxygen atoms sit here. Okay, so now how can we create bonding interactions or orbital overlap between the px and the py orbital of the oxygen and the 5s orbital of the tin? Okay, so now for these oxygen atoms here, well, the px orbitals would be able to make orbital overlap with the tin 1s. And for these oxygen atoms that actually sit here, the py orbitals would be able to provide sigma orbital overlap with the tin 5s. Okay? So now we consider only these and do not flip the algebraic sign of any of these and see what the bonding character of the resulting crystal orbital is. Okay, so you see that we do not flip the algebraic sign of these orbitals in y direction and also not in x direction. We also do not flip the algebraic sign of these orbitals here in y direction, neither do we in x direction. So what's the nature of the resulting crystal orbital? So you see that, and I should also point out here that of course we do not flip the algebraic signs of the 5s orbitals also, so we have them all with the same algebraic sign at point lambda. So now you see that we have constructive interference here and here between these p orbitals and the 5s, but we have destructive interferences between that p and that p and the 5s. So by geometric inspections, you can easily see that these bonding and these interbonding interactions cancel out. Okay, and that's of course true for all 4 unit cells. All right, now we would therefore say, well, the crystal orbital is a non-bonding crystal orbital. So now we have, however, also the possibility to flip the algebraic sign of all 5s orbitals. Okay, but you see that that also results in a non-bonding crystal orbital. Again, the interbonding interactions are here and the bonding interactions are here, but that leads to the same non-bonding situation. So now we get, due to these interactions, 2 crystal orbitals. Okay, so the first crystal orbital would essentially resemble the 2p orbitals of the oxygen as indicated here, and the other one would basically resemble the 5s orbitals of the tin. Okay, you can understand this better when you go back actually to the molecular orbital picture. So when you combine 2 atomic orbitals to form molecular orbitals, but the combination results basically in a non-bonding situation, okay, then your 2 molecular orbitals are essentially the atomic orbitals from which you wanted to construct the molecular orbital. So you have 2 molecular orbitals to consider in your molecular orbital diagram. So that translates to band theory also. Okay, so when you try to combine, well, in the extended solids, multiple orbitals of one kind with multiple orbitals of another kind, and the interaction is non-bonding, then that results in two crystal orbitals that are non-bonding. Okay, not necessarily these two crystal orbitals have the same energy, and in our case, the energies would certainly be different because the 2p orbitals of oxygen have a very different energy than the 5s orbitals in tin. Okay, so now let us go from the case of the position lambda to the case of the position chi. So that means that we should now flip the algebraic signs of the orbitals in x direction, but keep them unchanged in y direction. You see that this is the case here. So in y direction, for these orbitals, we do not change the algebraic sign, but in x direction, we change the algebraic sign. You see that this one here is flipped relative to this one, and this one here is flipped relative to that one. So by the same token, for a py orbital here, we do not flip in y direction, but we do flip in x direction. So this one here is flipped relative to that one. Okay. Now the same we have to do also for the 5s orbitals of tin. Okay, you see the algebraic sign of this tin is not changed relative to the algebraic sign of this tin in y direction, but it is changed in x direction. Here relative to here, and here relative to over there. Okay, now let's think about what is the bonding situation that results. So you see now that there are well, bonding interactions between these three lobes in that 5s, in interbonding interactions between this lobe here and the 5s. So you see here now that the bonding interactions dominate. And you see that this is the case for all unit cells. Okay, so overall, we would say that we would have a weakly bonding crystal orbital here. So again, we can also define the algebraic signs of the 5s orbitals the opposite way. We can make these two positive and these two then negative. Okay, you see that this also results in a weakly bonding crystal orbital here. All right, but this crystal orbital would have again majority 5s tin character, whereby this one here would have majority O2p character. Okay, finally we could go to the point M. So at point M, we would flip algebraic signs in x direction and in y direction for all the orbitals we will look at. So you see now in x direction for these two, the algebraic signs are flipped. You see that in this direction, for these two, the algebraic signs are also flipped. So for these py orbitals here, you see the algebraic signs are flipped in y direction, and they're also flipped in x direction. So for the 5s tin orbitals, we have also flipping of algebraic signs in y direction, as well as flipping of algebraic sign in x direction. So now what's the bonding character of the crystal orbital that results? You see that now actually all four lobes of all four p orbitals that overlap with the 5s orbital creates bonding interaction. And that's true for every unit cell. So you can therefore say that we have at the point M the most bonding crystal orbital possible. So again, we can flip the algebraic sign of, or define the algebraic sign of the 5s orbitals also the other way around, which is again shown here. So this, which was negative, is now positive. This is now changed from positive to negative. This is changed from positive to negative, and this is changed from negative to positive. But you see that this leads to a very different character now. You see that we have now only completely interbonding interactions, and therefore the orbital would be the most interbonding combination possible. Okay, so thus far we have only considered the interaction of the 5s tin with the px of O. Now in addition, we also need to consider the interaction between the 5p orbitals of tin with the 2p orbitals of oxygen. Okay, whereby we consider only sigma interactions only. So which orbitals can interact in a sigma fashion? Well, the px orbitals of oxygen can interact with the px orbitals of tin in a sigma fashion. So how do they do that at the point lambda? Well, at the point lambda, we do not flip any algebraic signs, neither in x direction nor in y direction. You see, they're not flipped here in y direction. They're also not flipped here in x direction. Okay. So now that results now in the most bonding possible combination. Okay, because you see that here there's only positive orbital overlap. So here there's only positive orbital overlap, and here there's only constructive orbital overlap. And that's also true for these two unit cells. Okay. However, we can also, of course, flip all the 5px orbitals of tin, and that's shown here. And that now results in the most interbonding situation possible. You see now that all the interactions are being interbonded. All right, so we have one crystal orbital which is completely bonding and one crystal orbital which is completely interbonding. So next we can go from the point lambda to the point chi. And as we do so, we must flip the algebraic signs in x direction. So you see that in y direction, they are remaining the same. But in x direction, they are actually now being flipped, okay? So this means that this one here is flipped relative to this one. This one here is flipped relative to that one for the 2p x of O. And well, this one here, the 5p x, is flipped relative to this one. And this one here is flipped relative to that one. So what bonding situation results from that? So you see that here we have bonding interactions. Here we have interbonding interactions. Here we have bonding interactions. Here we have interbonding interactions. So the same over here. Here we have bonding, here we have interbonding, here we have bonding, and here we have interbonding. So we see that in this case, bonding and interbonding interactions cancel out. So it is as though we would have only the 2p orbitals of O not interacting at all with the 5p of tin. So again, we can also flip the algebraic signs of all the px relative to this situation here. Now we have basically interbonding interactions here, bonding interactions here, interbonding interactions here, and bonding interactions over there. Okay. Same here, we have interbonding interactions, bonding interactions, interbonding interactions, bonding interactions. So therefore, also this crystal orbital is non-bonding. Okay, we can say that this is the crystal orbital associated with the tin 5p x orbitals only. Okay, you see that this is non-bonding, as well as this one is also non-bonding. But of course, the energies of these two will not be the same, because this one has an oxygen character, while this one here has tin character. Okay, finally, we can go from point chi to point M. So at point M, we would need to change all the algebraic signs in both x and y direction. So you see, in y direction, algebraic sign is changed. Now in x direction, from here to here, algebraic sign is also changed. And that's true for both the tin px as well as the oxygen px. So for the tin px, you see that this is flipped relative to this in x direction, and this one is flipped relative to this one in y direction. So what is the bonding situation that results? So we see that we have here bonding, here interbonding, here bonding, and here interbonding. So again, bonding and interbonding alternates, resulting in non-bonding situation. Okay, the same for this series of atoms here. We have here bonding, here interbonding, here bonding, and here interbonding. Okay, again, we can flip all the 5p x orbitals of tin around, and that's again shown over here. Does that change anything? Well, we have now the interbonding interactions here, but bonding interactions over there. Again, interbonding interactions here, bonding interactions over there. Okay, same here. We have interbonding, followed by bonding, followed by interbonding, followed by bonding. So again, that crystal orbital is non-bonding, but this crystal orbital has now, again, 2p character of tin, while this one has the 2p character of oxygen. Okay. Finally, we would also need to look at the interaction between the 2py orbitals for both oxygen and tin. They can also interact in a sigma fashion. So now here we look at the interaction at the point lambda. So at point lambda, no algebraic signs are being changed. Okay, see that here. As well as we go from here to here to here, and from this one to that one, for example. We see that this results only in bonding sigma orbital overlap. Okay, so therefore this orbital will be the most bonding orbital that we can think of. Of course, if we flip the algebraic signs of all the 2p orbitals, and that is shown here, we will create the crystal orbital, which represents the most interbonding situation possible. Okay, So the orbital, which has tin 5p character, will be completely interbonding, whereas the crystal orbital, which has oxygen 2p character, will be the most bonding. So now again, we can go from point lambda to point chi and change the algebraic sign in x direction. Okay, so you see now here in x direction, algebraic signs are flipped. In y direction, algebraic signs remain the same. So what is the result of that? Well, here we still have only bonding interactions, and here we also still have only bonding interactions. So therefore, we can say that this crystal orbital is also a strongly bonding crystal orbital. Okay. So if we flip all the algebraic signs of all the 2py orbitals, as shown here, then we create again an exclusively interbonding situation. In that crystal orbital will be completely interbonding. This one will have now 2p character versus this one will have 2s character. 2p oxygen character. So finally, we can go from the point chi to the point m. And now the algebraic signs of all the crystal orbitals in both dimensions will be flipped. So you see they are flipped here in x direction. They're now also flipped here in y direction. So now that leads to the fact that for this crystal orbital, we have here bonding interactions, here interbonding ones, here bonding ones, and here interbonding ones. You see that bonding and interbonding alternates, resulting overall in non-bonding, in a non-bonding situation. And when we again flip all the algebraic signs of the 2py relative to this picture here, we see that then we get interbonding interactions here, bonding interactions over there, interbonding interactions over there, bonding interactions over here. So again, a non-bonding crystal orbital results, whereby this one has, well, 5p tin character, whereas this one has oxygen 2p character. All right, so now we have all the knowledge to construct our band diagram, which would be the next step. But I see that we are running out of time, and therefore we will do the next step in the next class. And we can stop the recording